Hello and welcome to the 17th of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be the webcast moderator today. As I have previously mentioned, the idea to have these hour-long webcasts originated almost 3 years ago with the members of my NESC, GNC technical discipline team, who thought that they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community practice. We nominally hold these GNC webcasts on the third Wednesday of every other month at this same time, 2 p.m. Eastern. Please note that this webcast is being recorded and will be made available for subsequent viewing on the NESC Academy site in approximately a month. The link to the NESC Academy site can be found on the webcast registration page. I'm now very pleased to introduce today's speaker, Dr. Kenneth Lebsock. 20 years ago, when Ken started supporting NASA at the Goddard Space Flight Center, he had already accumulated an extensive background in the dynamics and controls of space vehicles based on his previous experience with commercial space, military space, and university space science projects. He has served as either a GNC engineer or the lead ACS engineer on several of the Goddard spacecraft programs, including WIRE, TRACE, AURA, and James Webb Space Telescope. Dr. Lebsock has supported NESC since 2005, and he currently serves as the deputy for the GNC technical discipline team. He is the author of numerous technical papers on the analysis, design, fabrication, test, and operation of spacecraft attitude control systems. The complete version of Ken's biography is provided on the webcast registration page. Ken's talk today is entitled Fundamentals of Linear Stability. I truly believe this is a fundamental webcast. Ken is going to be taking us back to some of the most basic material, such as gain and phase margins and the use of the Nyquist plot, that most of us were originally exposed to in our first course on control system theory. So I think you'll find it interesting in that respect. It's a real throwback. At the end of Ken's talk today, I will moderate a 10-minute question and answer period. You'll be able to submit questions to Ken via the webcast site. I will now briefly walk you through the mechanics of how to do that. If you look at the snapshot of the webcast panel now being displayed on the screen, you'll see an expanded look at the toolbar on the bottom right. There are two specific control buttons there on that toolbar which I want to draw your attention to. The first is the Ask a Question button, which is the third button from the left on the actual toolbar. At any time during the webcast, you can use the control button to submit questions to Ken. Please include your email address or simply your name and center location when you are submitting your questions. Because of the 10-minute time constraint for the Q&A period, Ken will most likely only be able to directly answer a few of the questions that he receives from the audience today. But as long as we have your email address or your name and center location, Ken has promised to respond to all the questions that he receives today. I encourage you to submit your questions as they arise during the course of Ken's talk, as versus waiting for the end of his presentation to submit those. The second feature on the toolbox I want to highlight for you is the volume control button on the far left. If you place your cursor over the speaker icon there, you can access the volume control slider and use that to individually adjust your computer speaker volume appropriately. And now at this point, I would like to turn the webcast over to Ken.
Thank you, Neil. I'm very pleased to be here today. We will be discussing stability of aerospace systems and how it is quantified. For simplicity, we will consider linear time-invariant, single input, single output systems. The basic function of negative feedback control is to stabilize the dynamics of a system. By stabilization, we mean that the behavior of the system will return to its steady-state condition after a disturbance. This presentation will compare frequency analysis methods of analyzing stability. It will also examine the relationship between stability margins and the sensitivity function. The sensitivity and complementary sensitivity transfer functions define the linear design of a control loop. There are a variety of trade-offs required to specify them. Active control is required for many aerospace systems to stabilize dynamics that are naturally unstable when subjected to disturbances. The open-loop transfer function that is without feedback, describes the natural dynamics. Gain margin and phase margin represent the tolerance to perturbations in loop gain and phase delay of a control loop that is closed by negative feedback. These stability margins can be found analytically by examining the open loop transfer function. It is helpful to understand the representation of the gain and phase margins on three different kinds of plots of the open loop transfer function. The Bode and Nichols plots definition of gain and phase margin are most commonly used. Their shortcoming is that they describe two isolated stability conditions. In contrast, the stability margin that is defined by the Nyquist stability criterion captures the stability boundary for conditions of gain and phase combinations. It is important to understand Nyquist even if the stability requirements for your system are expressed as gain and phase margins. We will now define the notation for the open loop transfer function of a linear, single input, single output control system. We will also define the closed loop complementary sensitivity transfer function and the sensitivity function. We denote G of S as the transfer function of the plant dynamics and C of S as the transfer function of the controller, where S is the Laplace transform. Later on, we will substitute S as J omega to describe stability in terms of the frequency domain. The variables going around the loop are X, which is the system output, D, which represents an external disturbance, either a force or a torque, N, which is additive measurement noise on the output X, and then the noisy feedback signal Y is compared to the command reference R to give the control system error E. Closed loop will be discussed in the next two charts, but all of the other charts refer to the open loop transfer function L of J omega. Performance requirements encourage that the bandwidth be high enough so that all expected commands can be tracked. However, this needs to be traded off against sensor noise rejection. The resonant peak just under the bandwidth is undesirable for performance and stability reasons. Note that T of J omega going to infinity as L of J omega goes to -1, which is a consequence of the Nyquist stability criterion. This seemingly simple equation casts a very long shadow. It is the basis of all stability analysis in the frequency domain. The sensitivity function is the ratio of Y closed loop to Y open loop. The maximum magnitude of sensitivity, capital M sub S, is undesirable for disturbance amplification and for stability reasons. Trade-off between these concerns depends on shaping S of J omega. The Bode integral of S of J omega is a powerful tool to help shape the sensitivity transfer function. This is discussed for the X29 in Gunter Stein's Bode lecture presentation, Respect the Unstable, which is included in the references that we'll give at the end of this presentation. Historically, the gain and phase margins were determined using Bode plots. The definitions of gain and phase margin give the dependence of stability on variations in gain or phase that are applied one at a time in the absence of the other. The gain margin and phase margin are defined at two different specific frequencies. They do not describe the degree of stability when both gain and phase are varied at an intermediate frequency. We really desire a stability margin that defines stability over a range of frequencies. We can determine the gain and phase margins from the three different ways to plot L of j omega. For instance, Bode plots are done in terms of the magnitude and phase of L of j omega as a function of frequency. Nyquist plots are of the real and imaginary parts of L of j omega. Nichols are cross plots of magnitude versus phase of L of j omega. All three of these types of plots are important when you go to consider stability of the system. The analytical calculation of gain and phase margin should be checked for sanity by examining the Bode plots. The frequency range of particular interest concerning resonances is in the range of omega pm to omega gm. Omega pm is always less than omega gm because, as we shall see later, this is where the stability boundary in the lower right-hand quadrant of the Nichols plot may be more vulnerable to modal resonances. Here is an illustrative example. This does not represent any particular physical real control system, but it's been chosen to illustrate some of the points that we're trying to make here about sensitivity at different frequencies. These gain and phase margins define loop stability at the omega gm and omega pm frequencies, but may be very misleading about overall stability. This is why it is especially important to carefully examine the Bode plots in the frequency range between omega pm and omega gm. In this example, there is a resonant peak in the vicinity of omega equals 0.7 radians per second. Undesirable close approaches are not always obvious in large-scale log-log plots over a wide frequency range. When the scale is blown up, it becomes even more obvious for this example that there is very little margin for deviations in gain or phase in the frequencies around 0.7 radians per second. The worst case stability occurs at a frequency indicated by the red arrows. It will be found later when we discuss the Nyquist plot. This illustrates why it is important not to blindly trust a simple algorithm that finds the gain crossover and phase crossover frequencies. It's important to look at the plots on the Bode plots. The Nyquist stability criterion is referenced to the Nyquist point, that is, when L of j omega equals -1. That is when the closed-loop complementary transfer function, T of j omega, goes to infinity. To avoid clutter, the figure on the right shows the locus of a generic open-loop transfer function, not the L of j omega used in the previous example. Recall that sensitivity is S of j omega equals 1 over 1 plus L of j omega. The vector from the point -1, 0j on the complex plane is the Nyquist critical point. The vector from that point to a point on the locus of L of j omega is 1 plus L of j omega and is of magnitude, absolute value, 1 plus L of j omega. The shortest distance from the Nyquist curve, L of j omega, to the Nyquist point minus 1, 0 of j, the critical point is s, lowercase s, subscript m, which is a measure of the stability. The next chart will help to clarify this point. This vector diagram helps to clarify the connection between the open loop transfer function and the stability margin. The L, the open loop transfer function shown here, is the one that we used for the previous example. It has a large loop just before it closes into the 0 point. Now, the stability margin is the length of the radius vector from the Nyquist point to the closest approach of the open loop transfer function, the minimum radius. That is the vector lowercase s subscript m in the upper left-hand portion of the figure. The gain and phase pair that occurs at omega equals omega m, which is the frequency of that closest approach, define the worst case stability for the system. Note that lowercase s subscript m is equal to 1 over uppercase m subscript s. That is, the Nyquist stability measure is the reciprocal of the maximum of the sensitivity function. A surprising result. It is often necessary to use two different scales on the Nyquist plot to show both the phase margin and the gain margin. This happens because large gain margins are represented by small distances from the origin. The Nyquist plot is convenient for representing distances from the Nyquist point rather than distances from the origin. The plot on the left-hand side shows what the phase margin is for our example. The phase margin is defined by the point at which the L of j omega curve crosses over a circle of radius 1 about the origin. The plot in the upper right hand shows the gain margin. Actually, it shows a quantity that can be related to the gain margin in decibels, and that is the crossover of the horizontal line, the real axis, and that is represented by a distance delta from the origin. The gain margin in dB is 20 log base 10 of 1 over delta. Again, these numbers of phase margin 68.6 degrees and gain margin 34.5 dB are the same as we derived by looking at the Bode plot. This indicates that we have a very stable system if we look simply at the phase margin and gain margin. However, this large loop in the left-hand figure does indicate that there is some concern about a close approach to the Nyquist point. These are very simple inequalities relating gain margin to the maximum amplitude of the sensitivity function. These inequalities are surprisingly accurate for well-behaved transfer functions, and they are very useful also even for poorly behaved transfer functions, where there are resonances due to slosh or structural modes. In the previous chart, we saw that the actual margins that were available in gain and phase did appear to be very large, but that the distance to the Nyquist point was very small. Now, typical specifications for maximum sensitivity magnitude are in the range of 1 1/3 to 2, which corresponds to gain margins of 12 dB and 45 degrees to 6 dB and 30 degrees. We've got to be very careful if the lower bounds of the gain and phase margins given by these inequalities are relatively small compared to the gain and phase margins found from the Bode plots, or just a simple analytical calculation of the crossover frequencies and the gain and phase that occur there. Now, this particular example was deliberately selected to illustrate the visibility on the Nyquist plot of the small stability margin associated with the example. Recall that this example open-loop transfer function has large gain and phase margins as determined by the Bode plots. The maximum of the sensitivity transfer function occurs at a frequency of 0.714 radians per second, which is just under the 3 dB bandwidth of 0.747 radians per second. This example illustrates why the stability margin should be used to quantify the stability of a control system rather than exclusively relying on the gain and phase margin. The numerical values used in this example were deliberately selected to make the calculations simple on this page. The maximum value of the sensitivity function was exactly 4. Consequently, the Nyquist stability measure is 1/4, or 0.25. This gives the equivalent of a gain margin of 2.5 dB, or not a gain margin. This gives the equivalent gain position for that closest approach of 2.5 dB and phase of 14.4 degrees. That is where the stability is the worst, and that's well inside what we had calculated for gain margin and phase margin. Analytical calculation of the stability margin is extremely simple. It is important to verify any measures of stability by examining the associated Nyquist plot of the open-loop transfer function. The third type of plot that is used for stability determination in the frequency domain is the Nichols plot. It is a cross plot of open-loop gain and phase. It is commonly used for control systems analysis of systems with known resonances near the control loop bandwidth. Using the same example as we have used in the other two plots, the L of j omega plot on the Nichols chart is very dramatically looped over towards the origin, which is at 0 dB minus 180 degrees. That's the unstable point. Now, even though the gain and phase margins are easily read off of the Nichols plot, that is where they cross the magnitude axis and the angle axis at 180, it is obvious that they do not describe the true sensitivity of stability due to combinations of gain and phase variations. Those are two isolated points, the gain margin and phase margin at those crossover frequencies, whereas the true minimum stability is back towards the 0 dB minus 180 point. And we have a big loop going back in that direction. There needs to be a stability boundary of some sort drawn between the gain and phase margins. Combinations of gain and phase variations that occur simultaneously must be taken into account. That is, we would like to refer back to the Nyquist stability criterion and see how it is represented on a Nichols plot. These are the loci of constant stability margins overlaid on the Nichols plot. We have 5 different values of Nichols of Nyquist stability measure from SM equals 1/4 to SM equals 3/4 shown on the Nichols plot here. The stability margin SM is the radius of a circular arc on the Nyquist plot with its center on the Nyquist point -1, 0, j. Now, when it's transformed into the coordinates of a Nichols plot, they appear as segments of a distorted ellipse. And that is a reasonable approximation to make for these stability contours of an ellipse that is pushed down somewhat away from the 0 dB line and is expanded out depending on how far the circle on the Nyquist plot is away from the Nyquist point. The locus of the open loop transfer function L of j omega, for our example, should not pass above and to the left of the specified stability margin contours on the Nichols plot. Now, we have a definition of what the requirement is for that particular system, and it is 6 dB and 30 degrees phase margin. Well, a temptation is to take a straight line from the from 30 degree phase margin down to the 6 dB crossover point and say that anything inside of that straight line would be unstable or would not satisfy the requirements. However, that simple approach is not accurate at all. The actual margins are easily read off of the Nichols plot as the points where L of j omega crosses the gain and phase axes. But often a straight line is naively drawn between these 2 points to define the stability requirements boundary under the assumption that the gain and phase errors combine linearly. That straight line assumption is not correct. The stability requirements boundary on the Nichols plot should be a stability margin contour similar to the ones shown on the preceding page. A stability margin described by a contour of constant stability margin in the Nyquist sense includes considerably more area than the linear approximation between the gain and phase margins. The use of stability margin contour, in addition to the gain and phase margins, is the recommended best practice for assessing the stability of a system. Even though the gain and phase margins are easily read off the Nichols plot, they do not describe the sensitivity of stability due to combinations of gain and phase variations. In this example, the purple curve is the actual stability boundary that describes stability due to combinations of gain and phase deviations from nominal. That particular curve is for SM equals 1/4. Recall that the lower bounds of the gain and phase margins analytically determined from the maximum sensitivity were 2.5 dB and 14.4 degree. These are the points on the Nichols plot where the SM equals 1/4 contour crosses the axes. The straight line approximation of the stability requirement, gain margin equals 6 dB and phase margin equals 30 degrees, is very misleading. That straight line approximation is the dashed red line proceeding upwards to the right from the minus 6 dB point to the minus 150 degree or minus 30 degree phase margin off to the right of the plot. That approximation would say that anything inside of the dashed red line would be unstable, and anything outside, below and to the right, would be stable, or stable by the requirements definition. Whereas in reality, the actual stability region is the SM equals 1/4 curve. Anything outside of that is considered stable for SM equals 1/4, but that does not satisfy the requirement of 6 dB and 30 degree phase margin. The closest approach to the unstable -1, 0J point on the Nyquist criterion occurs at an omega of 0.714 radians per second, yielding the simultaneous changes of gain and phase of 1.8 dB and 10.6 degrees. That is, if we had a combination of gain and phase of 1.8 dB and 10.6 degree, that would be our closest approach to the unstable point. This presentation has shown the relationship between stability margin and gain and phase margins. It has also emphasized the relationship between stability and the sensitivity function. Often on a program, you'll be given stability requirements specified in terms of gain and phase margin. You've got to remember that these are independent margins describing how much either the gain or phase alone can be varied before the system becomes unstable. These two margins are represented as separate independent points on the Nyquist plot. However, the true stability objective is to specify how close a system is to becoming unstable for any combination of gain and phase. This is compactly and precisely measured by the stability margin defined by Nyquist, which describes the closest approach of the open loop transfer function to the -1, 0J point on the complex plane of the Nyquist plot. Stability margin contours can be drawn on the Nyquist plot to show the Nyquist boundary of different combinations of gain and phase deviations that can be tolerated with a certain level of robustness and stability. The gain and phase margins, as well as the Nyquist stability margin connecting them, are defined in the frequency domain. The margins and the contour can be verified in the time domain simulations by injecting different combinations of gain and phase perturbations from nominal. They can also be verified in a physical control system when you use hardware-in-the-loop tests. The linear design of a control system is determined by two transfer functions, S of j omega and T of j omega, that are tuned to achieve several distinct goals. Note that decreasing the disturbance rejection transfer function at low frequencies also reduces stability. This presentation has focused on the relationship between stability and the sensitivity function. The Bode integral of the sensitivity function being a constant is an important tool for designing the sensitivity function. And one of our references will go into that as it describes the effort that was made to try to meet a phase margin requirement on the X-29 aircraft. That was the one with the wings swept forward rather than backward. There were physical limitations on how much of a phase margin you could get in the pitch control loop because the system was so inherently unstable. And those requirements had to be modified as a result of this Bode integral being a constant. The complementary sensitivity transfer function, which we normally call the closed loop transfer function, is very important for tracking performance. That can be improved, tracking performance can be improved by increasing the bandwidth of T of j omega. However, limiting the bandwidth by rolling off T of j omega at higher frequencies is necessary to suppress high-frequency sensor noise. So there is a trade-off between S and T, and one of the trade-offs involving S has to do with stability. Stability margin is simple to calculate and more accurately describes the stability of the system than the traditional gain and phase margins. One of the takeaway messages of this presentation on stability is that typically the maximum sensitivity should be in the range of 4/3 to 2, which is equivalent to stability margin, the Nyquist stability margin, being in the range of 3/4 to 1/2. Those typical ranges correspond to gain and phase margins of 12 dB and 45 degrees for and to 6 dB and 30 degrees, which is these two specifications are very common in requirements for control systems. One of the control systems references is one of the very best is the 2008 book by Astron and Murray at Caltech. The price for the hardcover edition of this book on Amazon is $62.49, whereas you can get an electronic version of it free from Google Books. It is an excellent book that covers all of the basic controls ideas that you will need, including going into the Bode integrals and advanced techniques. The best reference for becoming familiar with the Bode integrals is the paper by Gunther Stein, Respect the Unstable. This second reference is an application of control loop design in the frequency domain performed by Gunther Stein for the X-29. And his story about trying to meet the phase margin requirement for that aircraft is particularly informative. This IEEE article can be downloaded for free from the Guidance, Navigation, and Control Reading Room on the NASA Engineering Network. Thank you.
Well, thank you very much, Ken, for sharing your practical insights into this very fundamental topic of linear stability for single input, single output control systems. I think that was a great refresher for us all, reminding us how important this topic is and giving us another way to consider and evaluate stability with this single metric, the stability margin. I guess a a question for you right off the bat is, I'm pretty sure much of what you told us today, I'm 99% confident that much of this has been out there for many decades. I guess, what do you personally attribute to the fact that we don't see this stability metric used all that often, the single stability metric that you illustrated for us today? More often we draw the, on the Nyquist plot, we draw the diamond shape with showing the 6 dB and 30 degrees of phase margin, gain phase stability requirements, gain margin requirements, phase margin requirements. Why do you think it is people don't use the stability margin that you were just talking to us about?
Well, I think it's because the Nyquist plot appears to be containing a lot more information than is really really apparent to the person who's using it to design a control loop. The Nyquist plot will show loops in the lower right-hand quadrant indicating slosh or flexible modes, but those modes, when they come up close to the minus 180 0 dB point, are indicating that there is a stability issue to be considered. And because of the way that controls has been taught recently in the last few decades, it's a temptation for designers to simply take a straight line between the 6 dB point and the 30 degree point and say anything outside of that triangular area is stable. And I would blame this on the way that controls is taught at the fundamental level in colleges now, that there's much greater emphasis on advanced techniques of controls and less emphasis on getting through the basics and getting it out to practicing engineers. Now, there's so much more information that can be gained about stability by going back to the Nyquist plot, but the Nyquist plot doesn't seem intuitive the way the Nyquist plot does, and so most engineers don't use it that way. But I'm advocating now that in addition to the gain and phase margins, that systems engineers actually make an attempt to use a Nyquist stability margin requirement when they specify the requirements for a control system.
Okay, well, thanks, Ken. I tend to agree with you about the intuitive nature of the Nyquist plot, and perhaps we have gotten away from some of the basics, and this was, as I said, I think was a great refresher. Right now, I don't have any other questions for you at my fingertips, so I think unless you had some closing remarks, any other comments you'd like to make, I guess I will say one thing. I'll echo what you said up there on your reference page. The article by Gunter Stein on the Respect the Unstable, I think is, I think it's required reading for control system engineers. If you haven't read it, I suggest you do. It makes a good connection between, and I think it sets the stage for a lot of the multiple input, multiple output theory that that is out there now today, more modern approaches. I think he makes a nice connection between the almost the manual loop shaping techniques, and he does it in a nice graphical way. I think you incorporated one of his graphics, by the way, and he makes the connection to some of the more streamlined approaches or mechanized approaches for loop shaping. Anyhow, I'd urge everyone in the audience to take a look at that. If you read it a few years ago, read it again. It's a powerful article. Ken, any last comments, observations?
This was really a presentation for reminding practicing control systems and for systems engineers to become aware that there is a more important stability requirement that they should consider using in writing specifications for control systems. Thank you.
Right. I'd interpret that last remark. You've really been emphasizing that here. There's perhaps would you agree it's a more precise way to specify a stability margin as people lay down these GNC system engineers or project system engineers lay down the requirements for the control systems. This would be in one quantitative way of laying out that requirement. So we'll have to see if this gains some traction. But again, thank you for putting this briefing together and giving the webcast today. As I said before, it's going to be recorded and it'll be available on the NESC Academy site for viewing later. So let's move on. I would like to say that I am soliciting feedback on this particular webcast, if I can, and also on the overall series, our Fundamentals GNC webcasts. So shortly, an email will be sent out to all the audience participants, and it will provide a link to a brief and simple online survey form so that we can collect your feedback. Please be on the lookout for that. And please do take a few minutes to complete that survey and provide us some constructive feedback. We want to make these webcasts as useful and as informative and as relevant to the community as possible. So we need your help and your feedback to achieve that goal. And in addition, we'll also be sending out another email to the entire NASA GNC community of practice, providing a link to where Ken's recorded webcast can be viewed online at the NESC Academy. And that'll take place in about a month or so. Looking forward, at our next NESC GNC webcast, we're going to be privileged to hear from Dr. Tim Crane from the NESC TDT, and he's going to talk to us on the topic of fundamentals of numerical methods for GNC modeling and simulation. And that next webcast is scheduled for Wednesday, the 19th of November at our usual time of 2 p.m. Eastern. And we are planning our future webcasts to address topics of general interest to the community, as I just said. So if you have ideas for webcast topics, GNC webcast topics, or even better, if you're interested personally in presenting a webcast, please reach out and contact me directly. At this point, I will say this completes today's NESC GNC webcast. Thank you for participating with us, and I look forward to you joining us again in November for our next GNC webcast event. Goodbye for now.